Thank you, Thabit, and thank you everyone for coming to my talk. So this is the second talk I'm delivering for this seminar. And so some of the background material is going to be more or less an updated version of the previous one. And so my name is David Mohaisin, and I joined UCF about 5 years ago, where I have been an associate professor in the computer science department. And before coming to UCF, I spent several years in academia and industry alike. At UCF, I run the Security Analytics Lab, and I pursue research in the area of system security and online privacy with applications focusing on machine learning, IoT, augmented reality, virtual reality, malware analysis, and blockchain systems, and more recently, online safety, privacy, and security economics. I've developed a few courses at UCF, and among notable achievements, I have advised 21 PhD students, 13 to graduation, who ended up going to academia and industry, all while at UCF in the last 5 years. I've advised also 11 MS students, 12 bachelor students, and I helped establish a joint PhD program between UCF and Inha University in South Korea. So what is my research? Generally speaking, as I mentioned, I'm very interested in security and privacy in the general sense. And security and privacy themselves are not systems. They are features of systems. And the systems I'm interested in include blockchain systems. In particular, my group has been pursuing some cutting edge research on understanding the attack surface of blockchain systems and ways to reduce that attack surface, as well as new applications that can benefit from trust and properties of blockchain systems. We have been also working on the intersection of machine learning and security, particularly understanding the applications of machine learning for security of systems and the security of machine learning, particularly adversarial machine learning. We've been also working on network system security for critical infrastructure and new attack and defenses with white box capabilities. We have been also working on software system security to devise new program analysis techniques that can help reason about the security of programs and their intents, particularly when the programs themselves are changing over time. And concrete applications that I've been pursuing include malware understanding, online safety, AR, VR, security and privacy, authorship attribution, and privacy policy understanding. And the rest of this talk today is going to be focused on only one element of my research agenda, that is AR, VR, IoT security, understanding their security under various inference capabilities. And so the first, for the motivation of this work, and in the general sense, today's hyper-connected consumer demand convenient ways to reach information which will give rise to wearables, such as smart watches, fitness trackers, and augmented reality glasses. And wearables offer many features, including navigation, payment, activity tracking, entertainment, etc. And they provide also an easy to understand information to stimulate even higher consumer demand. As a result, we have a growing user expectations with the new features being introduced and limited time for deployment, which would result in poorly security and privacy considerations. So the goal of this work in general is to quantify this landscape of security and privacy in this application space and remediate if we have issues with it. And so many wearables in general are equipped with GPS capabilities for tracking activities, including exercise activities. And the collected data from those devices would oftentimes be visualized and presented to users to engage them further. And this data could be visualized in raw kind of fashion, like in location trajectories, or even in more abstract elevation profile kind of information. However, the uncontrolled sharing of geodata has significant risks. For example, it will allow for stalking and for even theft. As noted in one of our studies, oftentimes, particularly for exercise activities, the starting point and end point is a place that is considered a private attribute, like home, work, or school. And so to address this issue of oversharing, what service providers have been doing is to hide activity maps or provide fine-grained access control to the users. The question then becomes, would sharing the elevation profile alone, not the map itself, provide privacy? And so we tackle this question. To tackle this problem, we first start by looking into various adversaries in terms of knowledge and goals. To realize those adversaries, we formulate the goal as a learning problem. And given the input as an elevation profile, for example, in the problem statement earlier, we aim to predict the output as a SID location. It could be the exact location of a target, a specific target, or could be a borough of the target in a given city, or it could be the city of the target in a given country. And so to pursue this problem, we build a pipeline that consists of 4 stages: data collection, pre-processing, representation, feature extraction, and classification. And so for our data collection, to demonstrate this problem, we compile data set of a user-specific data set, a city level data set, and a borough level data set. And except for the user-specific data set, everything is obtained from open source maps like Google Maps and other available maps. For pre-processing, we developed 2 approaches for representation. One is image-like and one is text-like, with the appropriate encoding and word discretization. And we devised algorithms to automate the parameter decision based on general training loss as well as balanced fine-tuning. From there, extracting discrete features would be just using standard techniques like TF, IDF, and GRAM for text-like and convolutions for image-like. And for classification, we built a fine-tuned 2D CNN and use various off-the-shelf learning algorithms to kind of reach the goal that we try to attempt for. For the results, and for the interest of time, we show the accuracy metrics. And for the first threat model, using text features alone, we are able to predict the user location with 98.5 accuracy. And for the second, with the text features also, we are able to predict with 80% accuracy. And here in this figure, we are showing those results for a number of cities for TM2, and finally for TM3, which is the strongest adversary model. We are able to predict which city a given target is staying in when only sharing the elevation profile. Currently, my group is working on defenses, and defenses are, basically around aggregation and perturbation. For the interest of time, I will just move to the next topic, but we'll be very happy to discuss what we are doing right now on this. The second problem that we look into is looking into understanding the security, or particularly the privacy of AR elevation, the AR particularly. And so as we know, ARs today are AR HMDs, particularly the head-mounted devices, are available for consumers, including multiple offerings. And the features offered within recently available AR glasses allow diverse use cases, including simulation, entertainment, among others. And to basically fully integrate AR technologies, there has been a lot of efforts to develop a new type of input mechanisms that are convincing to perception, including voice commands, hand gestures, and gaze tracking. Hand tracking for input has been utilized for those air tabbing keyboards, and it's argued to be more private. And so the question that we try to answer in this research direction is, are air tabbing virtual keyboards basically secure? And so we start by formulating, again, threat models in which breaching the security is plausible. This includes various scenarios like planting a hand tracker and recording the victim's hand movement, or sitting near the victim, or infecting the victim's machine or HMD with malware. And then our pipeline is, again, 5 stages. For key tab localization, we leverage the fact that hands follow certain patterns while typing on AR keyboards to make a tab recognizable. And so we localize the pattern. Since we have access to only low tracking data, we pre-process the data to remove the dependencies, utilizing multi-headed CNN to generate confidence score that we use as our feature. For the key tab localization refinement to reduce even the problem space to be more tractable, we exploit the fact that tab points lay on a plane in 3D, and we try to estimate this plane and discard data that is not relevant. For candidate key center generation, we use clustering of the key observations into key centers. And then for candidate key reconstruction, we build transformation that cope with the change of coordinates in the observation space and map the key tab points to their AR keyboard. And for each possible tuple of 2 points in the space and the coordinate corresponding to the center and the key assignment that we have, we find transformation and form a candidate. Then what we do is that we rank the plausible keyboards in space based on their order, best to worst. And for that, we use various heuristics, including a scaling factor, plausible keyboards based on what is usable of a scaling factor of the virtual keyboard, outlier ratio, and the gap between the multiple numbers of unique keys and clusters in the training process. We feed all of those into a classifier and output the ordering score of the reconstructed keyboard and use that as the keyboard on which the observations would be mapped. So for evaluation, very quickly, and I understand that I'm 1 minute over time, we use the one hop accuracy as a measure. The H hop basically is considered as a key accurate if it is within that given number of hops of the correct key. And for end-to-end experiments, we use 4 data sets by 3 participants as shown here. And here, the main results demonstrate that, for the top 1, say for example, top 1 keyboard reconstruction, the H0 hub, that is the exact key, is predictable in the case of emails with 15% accuracy. And as you increase the number of the top candidates, and that is, in a sense, this is a privacy problem. So understandably, this low accuracy is meaningful in that domain. As for defenses, we have been exploring, and I have another PhD student working on this problem, exploring randomization, key jittering, and 3D projections, for example, on spheres and other objects for new keyboard reconstruction in virtual reality that are basically resistant to those kind of attacks. Finally, this work is mostly done by one of my PhD students, recent PhD students, Ulko Materials, who has since joined Facebook. But for all the work that I've been doing at UCF, I would like to acknowledge my 13 PhD students to date and the current 8 PhD students I'm working with, as well as the sponsors. This work particularly was supported by NRF and CyberFerd. With this, I'm very happy to answer any questions.